Welcome everyone to my talk. I'm Biswajit Datta. I'm a postdoc with Professor Vinod Menon in the City College of New York. Today I'm going to talk about designing a new Polariton system which is highly nonlinear based on bilayer MoS2 as a platform. So what are Polaritons? So Polaritons are hybrid excitations between light and matter. So typically, there are many ways of making polaritons, but in my talk, I'm going to focus on microcavity polaritons, which is made by sandwiching a material which hosts the exciton in between two mirrors. And under suitable condition, the trapped light inside the cavity strongly couples to the material resonance. In this case, it's an exciton, which is hosted by the semiconductor. And it results into two different new modes of the system, which are known as upper and lower polariton. Now, by itself, polaritons are very interesting because being a hybrid resonance of light and matter, it inherits different interesting properties from both light and matter. For example, they have very low effective mass, which is a consequence of being made of light. Also, they start interacting with each other, and that is a consequence of being made of matter. Now, TMDs are a prime candidate of making polaritons because of many reasons. Among different mechanisms, I'm going to focus on a particular property, which is nonlinear optical property. Now, traditionally, people have studied nonlinear property at very high pump power. Now, in our lab, we are trying to design a system which is very nonlinear at a relatively lower pump power. And by the talk, hopefully I'll convince you that interlayer excitons is a very good candidate to design such a nonlinear system. In particular, we focus on bilayer MoS2. But before we go to bilayer MoS2, let's study a little bit more traditional heterobilayer TMDCs, which also host interlayer excitons. So for example, when you lay a layer of MoS2 on a layer of WS2, because of type 2 alignment, charge separation happens between two layers. One layer has excess of electrons and another layer has excess of holes. And because of that, the resultant excitons attain a permanent out-of-plane dipole moment. While it's very good to tune the energy of this exciton by an external electric field, it has typically very poor oscillator strength, and hence it does not absorb light, which is no good for making polaritons. Now let's move to bilayer MoS2. Now, naturally occurring bilayer MoS2 has a very peculiar charge distribution. You see the electron is confined in one layer. However, the hole is free to move among both the layers. And this is at the heart of the nonlinear property. Now, because of this weird charge distribution, it has both out-of-plane dipole moment and an in-plane dipole moment. And because of this, it has a reasonable oscillator strength. And at the same time, the out-of-plane dipole moment can be used to tune the energy of this exciton. Now, on the bottom panel, the black curve shows the differential reflection at room temperature of monolayer MoS2, and there are two peaks associated with A and B excitons. The red curve is the differential reflection of bilayer MoS2 at room temperature. And you see there's a small peak between A and B excitons, and that is precisely the interlayer exciton, which we are going to focus in our talk. It has already been shown in the literature that this exciton is sensitive to electric field, and hence in a FET structure, you can actually provide external electric field and split this exciton into two, depending on electrons being on the first layer or on the second layer. These two excitons can have different energy at finite electric field. However, in our experiment, we do not provide any bias, and we show that even at zero bias, the interlayer exciton-polaritons are very highly nonlinear. So to make polaritons, we sandwich a layer of bilayer MoS2 in between two hexagonal boron nitrides and put that on top of a DBR mirror, and on top we deposit silver mirror. So, and we measure the differential reflection of the system at 7 Kelvin temperature, because at lower temperature, the interlayer absorbs more light. So we see in total 5 polariton branches. They come from 4 different excitons in the system, and we can model this system via a coupled oscillator model, which describes our system very well. Now, from now onwards, we are going to focus on a very particular branch of polaritons, which come due to the interlayer excitons. So we look at the differential reflection and increase the power of the system. And the increasing pump power excites more and more excitons, and we see what's happening to the differential reflection. So the 2 dips in the middle, which are marked by the dashed lines, come due to the lower and the upper polaritons of the interlayer excitons. We see they sort of come close to each other, and which is a sign of nonlinearity. But there are 2 different mechanisms of nonlinearity. The first is known as saturation. In that case, the 2 branches shift symmetrically towards each other. But in our experiment, we see the lower branch shifts more than the upper branch. And that can be understood when you take exciton-exciton interaction in the system. What happens because of higher density at higher pump power, the excitons start interacting with each other, and it normalizes their energy. And because of this combined effect of exciton-exciton interaction and saturation, we can we see the asymmetric shift in our experiment. Now we can track these dips in the polariton lower branch and upper branch and plot it as a function of polariton density. We see that the blue curve coming from the interlayer upper branch shifts lesser than the lower branch, and that is precisely we are talking about in the previous slide. Now, how much the branch moves is a measure of nonlinearity. So to benchmark the nonlinearity of the interlayer exciton-polariton, let's compare it with a regular exciton-polariton. In our case, in the same system, we have the bottom branch, which comes primarily due to the A exciton-polariton. So we compare it with A exciton-polariton, and again, we track the energy of this branch as a function of polariton density and plot the energy as a function of density. We see an interesting difference for interlayer exciton-polariton. We see the energy changes non-linearly with density, and the slope of this curve is the strength of the nonlinearity. So the strength of the nonlinearity changes with density for interlayer exciton-polariton. However, for A exciton, the energy changes more or less linearly with density, and hence the strength of the nonlinearity is more or less constant. Now let's actually take the explicit derivative of these curves. These are the same curves shown in the previous slide. The upper panel is the interlayer lower polariton, and the bottom panel is in the A exciton lower polariton branch. So we'll take the derivative of this curve and plot it as a function of density. Now, this is the strength of the nonlinearity, which is known as G factor. For interlayer, we see that as expected, the G factor is a function of the density. However, for A exciton, it's more or less constant. More importantly, At lower pump power or lower Polariton density, we see that the magnitude of the G factor for interlayer is almost an order of magnitude higher. Now, what does this number mean? To get a more intuitive understanding, we can define a number, and basically the number of polaritons per micrometer area, which is required to move the line width of the exciton by one line width. Now, in our case, the line width of this excitons are around 14 MB, and we divide that by the G factor, which tells you how many polaritons you need. So for interlayer polaritons, it turns out we need around 140 polaritons per micrometer square to change the energy by one line width. For A exciton, the same calculation gives us 1400 polaritons per micrometer square. Now that's a lot of polaritons. So here we can already see we have already improved the nonlinearity by an order of magnitude. We have also done measurement in open cavity, and we have seen that when we increase the pump power, both the interlayer and the A exciton saturates with pump power. However, the interlayer exciton saturates at a very lower pump power. So you see the oscillator strength goes to 1 to 0.2 within 80 nanowatt, but for A exciton, it takes almost an order of magnitude higher pump power to reduce the oscillator strength by same amount. This again verifies that the nonlinearity of the interlayer is intrinsic and its order of magnitude higher than exciton. Not only that, now we have established that this interlayer exciton is much more interacting. We can actually separate the two different parts, and to do that, we write the shift of the upper and lower branch at Rabi energy as a symmetric and anti-symmetric combination of exciton-exciton interaction and saturation. And we can do that because we see that for the lower polariton, the exciton-exciton interaction and saturation works in the same direction. However, for the upper branch, the exciton-exciton interaction and saturation works in the opposite direction. Now, we solve these two equations simultaneously at a given power and plot it as a function of power. We see that the exciton-exciton interaction is half of saturation. So saturation nonlinearity is dominating in our system. Now, microscopically, we also can understand why is interlayer so much nonlinear compared to regular exciton. And to do that, we look at some prior theory works. For example, in this PRB paper, it has been worked out that there are two different components of this energy. One is direct Coulomb and another is exchange Coulomb. So we first note that for regular excitons in monolayer TMDs, the exchange interaction is higher than the direct interaction. But what happens in heterobilayer TMDCs, which host the interlayer excitons? To go there, we first see that the magnitude of the exchange interaction reduces pretty fast with the electron-hole separation. So that means the exchange is negligible because the electron and hole separation is higher in interlayer excitons because they are in two different layers. So for interlayer excitons in general, direct term is more than exchange term. Now, what happens in our system, homobilayer? So as we already established that direct term is the dominating term in our system, in the same paper, it has been worked out that direct term is proportional to the Bohr radius to the power 4. And we expect that the interlayer exciton will have a higher Bohr radius because the exciton is in two different layers. And that is probably the reason of the observed tenfold enhancement in nonlinearity. We also note that in our experiment, we haven't provided any external bias, that means 50% of the excitons has dipole moment in one direction, and the another remaining 50% has the static dipole moment in the opposite direction. And hence, we also expect that in the further studies, when we apply the electric field in between two layers and create a true dipolar polariton, the observed nonlinearity may be even higher. With that, I thank you for your attention, and any questions are welcome. Thank you.